Alrighty, welcome back, everyone. In today's next session, we have our three papers, work in progress, starting with the LLM Honeypot, leveraging large language models as advanced interactive honeypot systems.
Hello. Yes. Okay. I'm Hakan. I'm a PhD student in the Information Science program at University at Albany, New York. And today I'm excited to present our research titled as LLM Honeypot, leveraging large language models as advanced interactive honeypot systems. This work was conducted in collaboration with my advisor, Dr. Canvas, in the AI in Complex Systems Lab. And this is originally published in IEEE Cyber Resilience Workshop. And since then, the field has seen significant growth, which I will touch on during the talk. And let's jump into it. Let me give some background. Honeypots are decoy systems designed to attract and engage potential attackers. It allows us to study their tactics, strengthen our security infrastructure. And however, the traditional honeypots have number of limitations. They have limited emulation capabilities. Even the high interaction honeypots can only simulate a finite set of behaviors. More critically, they are often vulnerable to fingerprinting, meaning experienced attackers can easily identify them as decoys and simply move on. This reduces the intelligence we can gather from these systems. And this is where the large language models come into play. Recent advances in LLMs, everyone knows how they work now. I'm not going to explain, but they can understand and generate human-like text, which directly improves the quality of interactions. And second, advanced models can maintain context over very long conversations. So if an attacker issues a sequence of related comments, the system can respond coherently, continue the conversation, and improve the realism. And third, LLMs can be fine-tuned on domain-specific datasets. It's creating a honeypot that can learn the language of real attacks and continuously improve over time. And since our paper was published, this area has grown rapidly. While preparing this presentation, I looked at the literature again. Those two papers, first two papers, Shell LM and Honeypot GPT, was there when we started this research, but the other ones are new. Basically, Shell LM and Honey GPT, they were using system prompts over ChatGPT API, very structured architecture, and they collected real-world field data, which was important, but they had some limitations. And after we did our research, I saw there are a couple papers published. If we quickly go over on them, LLM extended the LLM honeypots into industrial control systems, and other Gala and LDAP honeypot systems, they also introduced new protocols. This here is an interesting one from a company named Splunk. They did an industry adoption, published an open source SSH honeypot with an auto classifier. And the other ones also introduced new backends, new AI models. And finally, Valmes introduced new protocols again, and they also introduced agentic defense systems. The last one, systematic review, they did a systemization of knowledge and did a review of all the honeypot, LLM honeypot field. Definitely, you can check it out. And now, when we started this work, the existing research had significant gaps that motivated our approach. First, earlier studies relied primarily on prompt engineering, as I said, conversation history as context rather than fine-tuning the model. And prompt engineering alone has limits in terms of consistency and depth. And the second problem was they depended on closed source LLMs like ChatGPT, and this limits reproducibility since researchers cannot inspect or modify the model's internals, or it introduces a dependency on a third-party API. And third, existing approaches showed limited adaptability. This was also a problem. There was no mechanism to continuously learn from new attack patterns or incorporate previous interaction logs into future training. So our contribution was to address all three of these gaps simultaneously. We used supervised fine-tuning on an open source model with real continuous attacker data. So that was our contribution. These gaps led us to two research questions. Basically, how can LLMs be used to develop more realistic and sophisticated honeypot systems? And secondly, can we fine-tune LLMs to create honeypots and collect informative interactions compared to traditional systems? Our methodology consists of 4 key steps: data collection and pre-processing, prompt engineering, model selection, and supervised fine-tuning. I will walk through each one. Okay, for data collection, we gathered comments from 3 different sources. First, we parsed 174 real attacker comments from the logs of a publicly deployed Cori honeypot. So this is genuine malicious activity. Second, we compiled 160 common Linux comments based on the top 100 most used comments with some of their variations to make sure cover everything. And third, we added 283 command explanation pairs from directly official Linux documentations to give the model deeper understanding of what each command does. So basically, we are trying to develop a model to simulate a Linux server. So we came up with these pairs. For pre-processing, we combined these into a collection of 617 unique commands. We then run each command against the local Cori honeypot via SSH and capturing the actual terminal responses in a controlled environment. This gave us a clean data set of command response pairs. We also created a separate set of command explanation pairs, which I will also show the explanation later. Both data sets were tokenized and formatted to be used in the fine-tuning step. Next, the prompt engineering. Crafting effective prompts is important, as we saw in the earlier research. They define how the model behaves during inference. We didn't create these prompts from scratch. We built on prompts from the previous studies, did some refining and through iterative testing. For the command response portion, we designed a prompt that instructs the model to behave strictly as a Linux terminal, Linux server. Respond only with the terminal output, no explanations, no extra text. For the command explanation portion, we use a second prompt that positions the model as an expert and providing detailed explanations when asked. These 2 prompts made the model both simulate a server and understand the commands it's responding to. For model selection, we evaluated several recent models. They were recent at that time, not anymore. I believe the models are changing rapidly. These are already outdated. But we found out that like larger models, like 70 billion parameter variants, were too slow for real-time interaction. If an attacker has to wait 30 seconds for a response, they will know something is off. So we found out smaller, not small, but medium-sized models are the best ones. Strong proficiency, fast inference, and manageable hardware requirements. And notably, this finding has been validated by the recent research papers. They compared 13 different models, and they also confirmed medium-sized models are optimal for latency and accuracy. And so at the end, we chose Llama 3 8 billion as our model. For the fine-tuning, we used Llama Factory as our training framework with the curated dataset we had to make the training efficient on our hardware and also reproducible, make the code reproducible. We employed a couple optimization techniques. We employed LoRa, low rank adaptation, which reduces the trainable parameters by decomposing the weight matrices into lower rank representations. Basically, you don't need to train all the model parameters at the same time. You need a small portion of them. And even that layer is enough to fine-tune the model. We layered on a few additional optimizations like QLoRa, Neptune noise, flash attention to. QLoRa is for reducing the precision. When you use 8-bit precision, it significantly reduces the memory usage with the same accuracy. Neptune noise, we had a small data set, so we used the regularization technique to prevent overfitting, and also flash attention to speed up our attention mechanism, which is important for processing the command sequences. The entire training process took less than half an hour in our NVIDIA GPU at our lab. But I believe with these optimizations, you can also do it on your laptop as well. Our codes are publicly available. Now let's move to the experimental results. I will cover 4 things. The overall framework architecture, our custom SSH server, and training loss analysis, and also the similarity evaluation against a Cowrie real honeypot system. Since LLMs process text, not the network traffic, we needed a net wrapper to bridge that gap. Our architecture has 4 components. The attacker connects via SSH, and just as they would to any real server, an SSH server manages the connection, handles the authentication, and relays the commands. Behind the server sits our fine-tuned model, which processes each command and generates a response, mimicking a real Linux server. And finally, a logging layer records everything. We collect IP addresses, credentials, commands, and responses for the post-instance analysis. From the attacker's perspective, they are interacting with what looks like a normal Linux machine. But in the behind, we are collecting information from the attacker. And this architecture pattern, the front end, back end, and logging layer has become the standard design. In the review paper recently published, they identified it as emerging canonical architecture for LLM Honeypot papers across the field. So everyone is using our simple infrastructure design. For the SSH server component, we built a custom implementation using the Python language and some libraries. This gives us the full control over the interaction flow, how connections are accepted, how authentication is handled, and how commands are routed to the large language model. The server captures three categories of data: attacker's IP address, the username password pairs they attempt, and full log of every command along with the model's response. This design lets us mimic specific server behaviors down to the SSH protocol level, making fingerprinting significantly harder. And also it is possible to expand over this code base. You can implement other protocols or even simulate industrial control systems. This is training loss analysis of our model. This graph shows the training loss declining steadily over 36 steps. The consistent downward trend, it confirms the model is effectively learning from the dataset. It is progressively getting better at generating appropriate terminal responses. One thing to note, the training was fast, less than half an hour, which means this approach practical to iterate on. As I said before, if you collect new attacker data, you can refine tune and redeploy your models quickly. It is also possible to use this on the real world settings. Similarity analysis. So we fine-tuned the model, but somehow we needed to prove our model is fine-tuned model is better than the base model. To evaluate the performance, we compared our fine-tuned model against the base Llama 3 8 billion model using three different metrics over 140 samples. Cosine similarity, which measures the vector alignment between the expected and generated outputs. The higher is better. Jero-Winkler similarity, it's focuses on the character level matching. Again, higher is better. And Levenstein distance, the number of edits needed to match outputs. The lower is better in this case. So all three metrics confirms the fine-tuning is it enhances the model's ability to replicate real server behavior. And finally, we also compared the fine-tuned model's outputs directly against logs from a real Corey honeypot. This histogram shows the distribution of cosine similarity scores. As you can see, most scores are clustered toward higher values. Most of them are between 90% and 100%. It means that models' responses are closely match what a real Corey server would produce. Some outputs may differ slightly, but they remain contextually accurate. Importantly, the model handles edge cases really well. That's what we saw in our tests. When it encounters with unrecognized commands, it responds with realistic error messages, like command not found, and it maintains the persona even under unexpected inputs. To wrap up, our study presented one of the first approaches to honeypot design using a fine-tuned open source language model. And as I mentioned, this area has grown significantly since then. On the strength side, this system delivers accurate responses even to unusual inputs. It makes it harder for attackers to distinguish from a real server. And because it's built on an open source model, it can be easily retrained as new attack patterns emerge. On the limitation side, despite our optimizations, the system still requires a GPU for real-time inference, which may be a constraint in some deployment scenarios for now. In the future, it might be better. And the model's performance is tied to the quality and diversity of its training data. There's always a risk of bias toward the attack patterns we trained on. And looking at what happened since, the field is moving in several different directions. I saw multi-protocol frameworks. They simulate different protocols simultaneously. Hybrid approaches, they combine caching and do some optimizations in inference to reduce latency. And also there are some industry companies, they are building production-oriented tools. And researchers are even using honeypots to detect AI-powered attackers. So we are using AI to defend against AI, not just human ones. And thank you for listening. Our fine-tuned model was publicly available on Hugging Face, and the full code base is on GitHub page. On our GitHub page, I'm happy to share the links. You can reach out to me, and I'm glad to take any questions.
Hi, Hakan. Hey, excellent,
Yeah.
excellent presentation. That actually, coming from systems administration and engineering aspect, I thought this
Mhm.
was pretty interesting. To kind of kick off the first question, I wanted to know how well it would respond to command outside of something that might be normal. I know your point,
Mhm.
your pro said that it does respond to command and spits out a realistic error. But what if, for myself, I'm familiar with tools such as Ansible, where it's an agent list SSH tool and can set configurations almost like a bash script. But what if I'm chaining those commands? Have you seen
Mhm.
anything like that in your experiments?
Yeah, what we try to do is we scrape the Linux official Linux documentation, and we have all the commands available in our dataset. So uh, we don't have any suspicion, like it knows everything, it knows every command it needs to know. About the chaining commands, we have some chain commands in our dataset as well, but not much. I'm sure if you combine a couple different uh, commands as a chain, it will produce some errors. But as I said, it's the good thing is this fine-tuning process is scalable. So if you include more data into your data set, I believe your model will be better in the future. Yeah.
Thank you. Looks like we have one question in chat, starting with how well will your LLM honeypot respond to an attack that doesn't appear in your training data?
Yeah, as I said, the commands, it knows what command does what. I believe it will try to simulate what the result will be, but I cannot promise it will work every time. Especially we are using smaller models here, like 8 billion language models. At this point of time, I believe it's easy to trick them. But I'm sure in the future, when we start using larger models and with faster inference times, uh, they can answer very difficult prompts as well, the commands as well.
Awesome, thank you. Another question would be, I know other tools such for model serving, such as Olama or VLLM, has
Mhm.
capabilities of adjusting temperature and tokenization. Are
Mhm.
those parameters that you've adjusted?
Yeah, we kept the temperature really low. We needed to get consistent responses. But even though you set the temperature to 0, these are not deterministic models. So it's possible to get different results. Yeah, I think there's definitely a gap of improvement over there. Yeah.
Understood. Thank you. Another question here.
Mhm.
How much latency is based on network conditions versus model compute time?
The model we used, Llama 3 8 billion, it's really fast. It feels like a real Linux server. You wouldn't feel the difference that much, but this comes with a limitation. This is not a very smart model. If you use a larger model, there will be a latency problem. That like it's a trade-off, yeah. But our model doesn't feel like slow.
That's a good note.
Mhm.
Looks like that is our time. Thank you very much, Hakan, for again your presentation
Thank you.
and speaking with us today.
Yeah, thank you.